This video is for IB. It's going to be sections H and I. H is on sets and Venn diagrams, and I is on laws of probability. So the Venn diagram, you're going to see we usually use a rectangle. Let's go with a better color. And the entire set is the universal set U. And like say if you had 50 elements total, you would put 50 out here. And then say inside you had a set of A items, like maybe, I don't know, I can't even think right now. Anyway, oh, the A you could write here actually is the best place to put it. I often put it outside. A, and then, so everything inside of the circle is in the set A, and everything outside the circle is the complement of A, which is A prime. And we already know that the probability of A plus the probability of A prime is 1. Some other notation is, I was already using some of these words, element. So X is an element of set A. Like say set A was the number, like odd numbers, 1, 3, 5. So this means X is an element of set A. N of A simply means the number of elements in A. So in my case, I've got 3 numbers in there, so that would be 3. And then if we had 2 sets, say we had set B, and it included odds, and let's say, how about 10 and 20. So if we had A intersect B, that's the intersections of sets A and B. Those are the elements that are in both A and B. In both. And in this case, that would be 5. And then A union with B would be all the elements that are in set A or in B or in both. If we were to list them for this particular example, they would be everything 1, 3, 5, 10, and 20. And another way the book, I was just writing this down, another way you can write this is you can say X such that X is an element of A and X is an element of B, using set builder notation. Disjoint sets are also mutually exclusive. That means they don't overlap. A disjoint means same thing. So disjoint or mutually exclusive sets would look like that. And what's the intersection of A and B? There isn't one, so it's the empty set, and that's how we write empty set. O with a slash through it. Example 15, suppose A is the set of all factors of 24 and B is the set of all factors of 28. And U, the universal set, is, so X is between 1 and 28, and X is an element of the integers, and that's the big Z. So letter A, find, oh yeah, and I have to write this. So this is find A intersect B, then we're going to draw a Venn diagram. Actually, I'll probably do that first. And then the last question is A union with B. So I'm going to start off by drawing a Venn diagram, probably fairly large because there's a lot of numbers between 1 and 28, and we have to include all of them. To save your time, I've worked this out ahead of time. A is the set of all the factors of 24, so you start with 1 and work your all the way up to 24. And I went through and did this on my own. If you want to take time to do that, you can. But I will just tell you that the Venn diagram, so first of all, actually what you can do is you can start with the ones that are both factors of 24 and factors of 28. 1, 2, 4. I can just think of those off the top of my head. And actually, you know what? Those are the only ones. And then additional factors of 24 here in set A that aren't in the intersection here. And like I said, to save time, I'm just going to tell you what they are. 3, 8, 6, 12, and 24. And then over here we have 7, 14, and 28. Those are the additional factors of 28. And then out on the outside we need all of the other ones. So technically you would have to go through and still like 1, 2, 3, 4, 5, 6, 7. Whoops, 7's already there. 8, 9. This could be turned into a 9. And so on. And you're going to have a whole bunch of numbers out here. Everything else between 1 and 28 that's not included in here needs to be listed out here. To save your time, I'm not going to take up time to do that. But just know that they are going to be all out there. And we don't actually need them in order to answer this question. A intersect B is everything in common, so that's 1, 2, and 4. It's the ones that are in both A and B. So letter A, I'll just say, we'll do it in set notation, 1, 2, 4. We'll just list them in curly braces. B is here. C, A union with B. You're going to list all the elements in A and as well as in B as well as in both. 1, 2, 4, 3, 8, 12, 6, 24. And if we had time, I would do them in order, but again, I'm not going to take your time to do that. So this gives you an idea of how that works. I am going to be skipping some of the easier examples, so you're free to go look in the book at those. So we're going to skip ahead to example 19. And this is not necessarily difficult, but I just thought it might be good to do this one. Let's make a Venn diagram to start with. That's why I left all this space here. In a class of 30 students, so 30 is the universal set. I'm going to put the 30 out here. We've got physics and we've got chem and both. So here's physics, here's chem. And what you want to do with these is you want to, ideally, hopefully, they tell you both. Although if they don't, there's a way to figure it out. But if 15 study both, that's what you want to start with, the intersection of the set 15. And then you can work backwards and figure out what goes here and here. There's a total of 19 in physics. Well, 15 of them are here. That means there are 4 left that are in physics but not in chemistry. So that's this portion. And then 17 study chem, so 15 are there. That means there's 2 left over. And then it's also handy to figure out how many are left over altogether. So you've got 19 plus 2 is 21. 21 from 30 is 9. So you can put the complements of P union with C out here. Now we can answer the questions. Probability that a randomly chosen person studies both. Well, then it's very easy. That's going to be 15 out of a total of 30, which we know is 1/2. At least 1, so that could be these numbers here, 4, 15, or 2. Any of these people in these areas is studying at least 1. So what is that? I think I said that already. Wasn't that 21? Yeah. 21 out of 30. That reduces to divide by 7. So 3, 10. Or no, it doesn't divide by 7. What am I thinking? I divide by 3. Divide by 3, you get 7 over 10. Physics, but not chemistry. So those are the people here, the 4 people. There's only 4 people that study physics, but not chem. 4 out of 30, and we can reduce our fraction. Divide by 2 is 2/15. D, probability of exactly 1. So that's just these 4 and these 2. So that's 6 out of 30 is 1/5. And neither, that's where the 9 came in handy. So, or did I do that right? Last in my notes here I have 7. Maybe I didn't do the math right. Let me check my math again. So that's 19, 21. Yeah, I just didn't do the math right when I did this on my own. So it should be 9 out of 30. I have 7 for some weird reason. So I'm going to switch that, fix that real quick here. Should be 9. Okay, doke. So I'm just going to check here and see. Yeah. Divide by 3. Okay. Great. So that one's done. Number 20, example 20, it says verify that A union B, the complement of that is A, the complement of A intersected with the complement of B. Now the way you're going to do this is you're going to draw a Venn diagram to show, actually it'll do each one. So we'll do 2 different Venn diagrams. I'm going to do A and B. I'm going fast so it's sloppy. And sorry. A union B is all this part, but we want the complement of that. So that's everything but that. So unfortunately I have the highlighter. I'm going to be shading everything outside of those two circles. Then, so that's the one on the left. Then on the right, I'm going to draw the same Venn diagram again. Maybe not quite as sloppy. And I'm going to shade the complement of A. So we're going to intersect the complement of A with the complement of B. So first, since I have a highlighter, I can do the complement of A. Let's make it be orange. So that's everything outside of A. The whole orange region. And then let's do this gray, how about? The complement of B is everything outside of B. Oh, you can barely see that, but you can see it well enough, I guess. That's all of that is gray. And then the intersection of those is where they overlap. So that's going to be yellow. And you can see they overlap out here. All out here. They don't overlap inside of B, and they don't overlap inside of A either. So the yellow portion is where they overlap. And then we can compare these two figures and see that the yellow regions are identical. And that was H. Well, that was short and sweet. Now we're going to do laws of probability. First one is the addition law, which I do believe I've mentioned before. But it says the probability of A unioned with B, so A or B, is the probability of A plus the probability of B minus the probability of both A intersect with B. Because you can't count the overlap twice. If you did probability of A plus probability of B and they overlapped, you'd be counting the intersection twice. And so that's why we have to subtract out one of those intersections. This will also work if it's disjoint, because if it's disjoint, what's the intersection? It's 0. So you're just finding the probability of A plus the probability of B. So the same law will work. Example 21 is on probably the next slide, yes. Oh, and I have to add in some stuff here. This is the union. This is intersection. Okay. So let's draw... Oh, actually, no, we don't need a Venn diagram because I think we have enough information here. It says find probability of B. And you can kind of get a sense from looking at the given information that this is going to be just simply using the formula. So let me bring up that formula again. Probability of A unioned with B is the probability of A plus the probability of B minus the probability of the intersection. And this formula, I do believe... You know what? Let's check on 11. I think on slide 11 I might have copied the formulas you get. Nope, I didn't. It's on a different one. Never mind. On your formula sheet, I'm pretty sure this is on there. So you have a choice. You could we could solve for B right now, or you can plug numbers in and then solve. Maybe I'll just plug numbers in. A union with B is 0.7. Probability of A is 0.6. Probability of B we don't know. And A intersect B is 0.3. And so then you just solve, what is that? Minus 0.3, 0.3. It's going to be 0.4. And that one is done. Mutually exclusive events, we already saw. Oh, I just talked about those. The same law will work, but you could also shorten it to just probability of A plus probability of B because the intersection is 0, or the empty set. Example 22 you can look at on your own in the book. It's fairly easy. And then the conditional probability. Now this is can be challenging. The conditional probability of A given B is the probability that A occurs given that B already occurred. And, oh, I'm so sorry. A given B. That's how you write it. That's read A given B. Example 23. In a class of 25 students, 14 like pizza, 16 like coffee, 1 likes neither, 6 like both. You read that information and that should scream to you Venn diagram. Notice it doesn't even say to draw a Venn diagram, but this is a very typical Venn diagram problem. One student is randomly chosen. What's the probability that the student does these two different things? So part of the thing with these, as we're going along here, is recognizing what technique to use. Should I just use a formula? Should I use a Venn diagram? Should I make a tree diagram? And you can try one technique, and if it doesn't work, you can try another. But those are some of the tools available to you. So we've got pizza. We've got coffee. And again, you want to, if you can, if they give you the information, the ones that like both, start with that. 6 like both. 1 likes neither. That's going to be out here. And 25 students total. That's going to go out here. 14 of them like pizza. Well, we already know 6 like both, so that means, oh, not 10. Sorry, I don't know what I was thinking 10 for some reason. 14 minus 6 is 8. And then 16 like coffee. 16 minus 6 is 10. So that's how you want to do that. And then you can answer the question. What's the chance that the student simply likes pizza? Well, there are 14. So this is A. 14 out of a total of 25. So that probability is very straightforward. Now the next one is a little more interesting. The probability they like pizza given that she likes coffee. So there's actually a formula for this. I'm going to do it intuitively first, and then I'll tell you the formula. So we are given she likes coffee. That's already known. So how many people like coffee? 16. So that's going to be the denominator, because we're only considering the people that like coffee, not the entire 25 people. And then out of those people that like coffee here, how many of them like pizza also? 6. So it's 6 out of 16, which reduces to 3/8. So the formula, the probability they like pizza given they like coffee is, here, let's just kind of discover it. 6 is on top. 6 is the intersection of P and C. So P intersects C. And then on bottom, we had 16, which was the probability of coffee. And oftentimes you'll see this written, they'll solve for the intersection, and you'll see it written P intersects C is P, probability of P given C times the probability of C. So you'll see it written both ways. To me, this first one is intuitive, the second one not so much. You will need to look at your formula sheet, and I know there's 4 laws that are given. I know this one is given, I think it's given in this form. So you need to be familiar with it and the fact that this can be, solved and used here. Moving right along, example 24. I've got a star by that one, it must be interesting. In a class of 40 students, 34 like bananas, 22 like pineapple, and 2 dislike both. Notice they don't tell us how many like both bananas and pineapple. That's probably why I started this problem. Make a nice big Venn diagram here. So we've got the banana eaters, and we've got the pineapple people. And we have 40 people total, so that goes out here. We have 2 that dislike both, so they're the complement of those bubbles. And now we need to think. 34 of them like bananas. So that means if there's 34 here, maybe I'll do my highlighter. 34 there. And the complement of that yellow region is everything out here. I know I have a total of 40. Plus, but there's these 2 here. So that means that there are 38. Okay, so that means I'm down to 38. But then 34 of them are inside of here. So that means there is 38 minus 4 will be left here in this part right here. So this is 4. So what I did to do that is I did 40 minus 2. That gave me 38. values that are going to be in both P, the union of P and B. And I already know that there are 34 of them in the banana area here. So that means there has to be 4 here. I'm going to attempt to erase the highlighter, at least to some extent. That's probably good enough. Cool. Now I know. Oh, okay. So 34 of them like banana. Oh, shoot. Did I do that? I think I did that backwards. Darn it. 34. Did I do that right? 34 like bananas. Yeah, that's right. 34, 38, 39. Yeah, it's good. I didn't do it backwards. 22. So if 34 of them like banana. Okay, yeah, here we are. So 22 like pineapple. 4 of the pineapple eaters are here, so there's 18 other pineapple eaters, and they have no choice but to go right there. And then I can work my way over here. I've got 34 that like bananas, 18 of them are right here, so what is that? 10, 14, 16 left that like bananas, but not pineapples. And this is how our Venn diagram should look. Now we got the hard part done, we can pretty well easily go through these probabilities. The probability that a randomly chosen person likes both, well, that's going to be 18 out of 40. And you know what? Just to save time, to save your time, I'm not going to bother reducing these. Probability they like at least one. So that's going to be these people, and these people. If you add all those up, that's 38. It should be, right? Because there were only 2 others out of 40. So 38 out of 40 will like at least one. They like bananas given they like pineapple. So that means I'm going to do it intuitively. Over here, all my pineapple eaters are right here. There's a total of 22 of them. And out of those, the probability they like bananas, there's 18 of them out of the 22 that like bananas as well. You're also free to use the formula for that as well. D, dislikes pineapple given he or she likes bananas. So here's all the banana eaters. 16 plus 18 is 34 of them. Now of these, how many dislike pineapples? That's going to be 16 of them. And of course we would reduce all these if we wanted to take the time to do that. And I do believe that, yep, this is our last one. Oh, I like this problem for some reason. So let's read it. The top shelf of a cupboard contains 3 cans of pumpkin soup, 2 cans of chicken. Bottom shelf contains 4 of pumpkin, 1 of chicken. Lucas is twice as likely to take a can from the bottom shelf as the top. Suppose he randomly chooses one. What's the probability it's chicken? Right away when I read this, I think tree diagram. For one thing, it's kind of like you're choosing a jar, and then you're out of each jar, you're picking a marble. And we use tree diagrams for those. Same deal here. So first, he's going to have to choose a top or bottom shelf. So top, bottom. If he chooses the top shelf, he is going to choose either pumpkin or chicken. Same with bottom, it's pumpkin or chicken. Now we can throw the probabilities on there. Let's see. Lucas is twice as likely to take a can from the bottom as the top. So it's a 2 to 1 ratio. So you could do 2x to 1x ratio basically. And that means for a total of 3. So this is going to be I'm trying to think of how to explain this. 2 to 1 ratio. So you know how if you have a 2 to 1 ratio, you can multiply each of those by x. And then you could think about the total is 3x. So this bottom one is 2x out of 3x, and the top one is 1x out of 3x, or 1/3. So what it boils down to is the bottom shelf, and I'm just rereading to make sure I did that right, 2/3 chance of the bottom and 1/3 chance of the top. That's just the way I thought of it. If you think of it another way that works for you, then that's just fine too. Now, if you're on the top shelf, you've got 3 out of 5 chance of getting a pumpkin, 2 out of 5 getting a chicken. Bottom one contains 4 cans pumpkin out of 5 and 1 out of 5 chicken. We've got the hardest part done, in my opinion. We've got the tree diagram figured. Now, what's the chance that if you randomly choose a can, it is chicken? That's going to be either this branch or this branch, so we multiply along the branches and then add them. So 1/3 times 2/5 plus 2/3, I am doing chicken, times 1/5. I'm going to keep my denominators. I'm going to have 2 plus 2, 4/15 for the probability of getting chicken. Okay, next. Probability, if you randomly choose a can, that is taken from the top given that it's chicken. So what's going to go down in the denominator? The chicken. The chicken ones are this one and this one. Well, we just figured that out actually, didn't we? That was right here. So that can go down in the denominator. We'll use that work. And then what is the probability that the can is taken from the top? So we need to, out of the chicken ones, which is this one and this one, only this one was on top, so 1/3 times 2/5. If you want, if you don't like just thinking about it, you can use the formula. So the probability that it's from the top given chicken is the probability of the intersection, top and chicken, over the probability of chicken. And then top and chicken is this one right here, the 1/3 times the 2/5, and the probability of chicken is the one we just figured out up there. So when we flip these, 15 over 4, that's a 15, we get 2/4 or 1/2. And that concludes this little guy.